Also, happy Halloween, in case you already forgot. Today, I'm going to talk about this sensing as a service. Everybody probably heard about the software as a service. Its acronym is like SaaS, okay? So we decided to call the sensing service, we give an acronym S square AAS because we thought that would be cooler than the software as a service, okay? So this is a joint work with my two of my PhD students, Mr. Xiang, Mr. Xuejie Xiao, and also my longtime research collaborator, Dr. Guoliang from Arizona State University. So here's the outline of my talk. So first of all, I want to point out that this paper is actually not a regular technical paper. It's more like a precision and a vision paper. So basically what we do is we try to introduce this concept, sensing as a service. And also we point out, we describe all the research challenges related to for developing such a sensing as a service cloud. And also we review all the existing systems and the solutions. And also the last but not least, we point out the future research directions. So this is the outline. So first of all, I will give an introduction to almost everything. Then after that, I will touch upon three specific topics, including the system design and implementation. The second one is energy efficient sensing task management, and the third one is the incentive mechanism design. And the very last one, I will point out the future research directions. So first of all, our vision. Okay, so I guess when you see these slides, everybody is wondering who is this guy. Okay, I believe most of the Chinese audience know who he is. His name is actually Jian, also known as God Erlang, Sheng in Chinese. All right. So just in case you don't know about him, in the Chinese mythology, this guy is actually a very famous figure. His mother is a sister of the Jian emperor, who is actually the Chinese version of the Zeus. Okay, so she married regular people, then he was born, so that makes him a demigod. Okay, the only thing, actually I can talk about him for the whole afternoon, but I don't have sufficient time here. So the only thing I want to point out here, as you may notice, that this guy has like the three eyes, This is like a one special eye, also known as this sky eye, right in the middle of his front head. Okay, and this eye is very powerful. Okay, it has this long distance vision and also has many other functionalities which I probably don't have time to introduce. But our vision is to offer every person a third eye, such that it can extend his or her sense to every corner in this world. That's our ultimate goal. It's a very big kind of ambitious vision. Then how are we going to do that? So our approach is to develop a unified, of course, I will describe what do I mean by unified later. Okay, and green of course means energy efficient cloud computing platform for the mobile phone sensing, and we actually call a system third eye. We actually already developed the system. We did some field tests, but today I'm not going to present that because that paper is still under submission. But this is our big vision and the basic approach we're going to take. So first of all, just want to give you a quick background introduction about the mobile phone sensing. As you may know, you probably didn't even notice, but most of the current smartphones are equipped with a rich set of sensors. Okay, this is a picture of I believe this is iPhone 4. Okay, including all those sensors here, like a GPS, cameras, accelerometers, microphone, digital compass, gyroscope. Those sensors actually can also can be used to sense and provide sensitive data for the users. And also, I want to point out, the application does not have to be restricted to those sensors on the cell phone, on the mobile phone. Actually, as you may know, many external sensors can be attached to mobile phone through this Bluetooth interface. For example, like 2 weeks ago, I was talking about with a professor from mechanical department, and he was talking about some sensors which can be used to sense the environment, detect the pollution, air pollution. Okay, it can be attached to a cell phone through this Bluetooth interface. So usually, two kinds of mobile phone sensing paradigm. Okay, the first one we call it participatory sensing. In this scenario, basically the mobile user actively engage in all the sensing activity, or in other words, all those mobile users, it manually determine when, where, what, and how to sense. Okay, typical example is like if you want the mobile user to take a picture for you, then basically this is a typical example for the participatory sensing. The second scenario is we call it opportunistic sensing. Basically, in this scenario, the sensing activity are fully automated without the user's involvement. Okay, and for example, if you just want to sense some Wi-Fi signal strength, you can just turn that Wi-Fi interface on. Then it will just automatically sense and report the data back to the cloud. So that's actually a typical example for the opportunistic sensing. Okay, so next, this is actually the basic idea of sensing as a service, S2AS cloud. So basically, this cloud somehow, on one hand, is somehow like similar to the other type of cloud. You may know those software as a service cloud, or infrastructure as a service cloud, or maybe platform as a service cloud. Because basically, in this cloud, we have to have the data center, and in the data center, we have to have those we call it the sensing servers. Okay, of course, you can have many sensing servers, many different data center which can be deployed in different places, because a cloud, this cloud is supposed to provide a service for the user from every corner in this world. And also, however, this on another hand, this cloud is different from other type of cloud, because for most other cloud, the mobile user are simply just users. Okay. For example, like you want this software as a service type of cloud, like this Gmail, okay, is a typical kind of software as a service cloud service, okay. So basically, the mobile user turn on a map in its mobile phone and get an email, from the cloud. So, however, in our cloud, those mobile users are actually part of the cloud. Okay, it's a component of this cloud. It's not just simply a user. However, of course, it can also be a user, because the sensing request can also be initiated by a mobile phone. So basically, this is the workflow of the sensing as a service cloud. Here, suppose we have some cloud user. Of course, like I mentioned before, those cloud user could be some desktop, the regular computer, or even the mobile phones. And those cloud user send some sensing request, okay, to the cloud. And those sensing requests, first of all, will reach those sensing servers. And the sensing servers will push forward those sensing requests to a subset of a mobile phone which happen to be in the area of interest. Okay, because most of the sensing applications are actually location dependent. Okay. Then those mobile phone sensors, will fulfill those sensing tasks. Get whatever data the cloud user want, and report the data back to those sensing servers. And the sensing server will, push forward back to the cloud user. Of course, for some especially important, interesting data, we may need to store them in the cloud, in some storage devices in the cloud. Okay, so like I mentioned before, the most interesting thing about this cloud is just those mobile phones, and they are part of the cloud. They are components of the cloud. All right, so here's some research challenges we identified, for developing and deploying such a sensing as a service cloud. Okay, the first one, we found out that we need a unified platform. Okay, here by unified, I mean it must be able to support a different kind of a mobile phone sensing scenarios applications. Okay, because most of the current work, previous work on the mobile phone sensing, they only target a particular application. Okay, like the group of researchers from the Dartmouth College, they mainly focus on, they call it people-centric sensing, try to sense the people activity and report back to the cloud system. Okay, and another group from UCLA, they mainly focus on environmental sensing using those mobile phones. Okay, however, we are trying to develop a unified platform which can provide any kinds of mobile phone sensing service, not only the participatory sensing but also the opportunistic sensing. And also, this platform should be able to support different kinds of smartphone platform. Okay, because the success of this sensing as a service cloud mainly depend on the population of the mobile user who are willing to participate in sensing activity. Okay, and if you have a large number of such users, then they may use different kind of a mobile phone, like iPhone or the Android phone, or maybe Windows phone, whatever. Okay, so our system need to be able to support different kind of smartphone platform, and also it must be energy efficient. Okay, this is easy to understand because still the main job, the main functionality of your phone is to make a phone call, to receive email, check email, or maybe browse the internet. Okay, it's not to sense. Okay, so if it's not energy efficient, then sometimes you may end up with an awkward situation in which that you want to make a phone call, you find it's out of battery because all your energy are used for the sensing, mobile phone sensing. That's a very awkward situation we try to avoid. Another interesting problem is this, we call it the incentive mechanism design. Okay, no free lunch. I guess this is the number one rule, not only in the United States, but around the whole world. Okay, so I mean, you cannot assume that all the mobile users will be volunteer to perform all those sensing tasks for you. Okay, because performing sensing tasks are going to consume their phone's energy and other computing, like computing resources. And also, more importantly, performing those sensing tasks may expose those mobile phone users to some security or privacy breach. Okay, so the system need to provide some kind of incentive to motivate the mobile user to engage, to participate in those sensing activities. So those are three main challenges we identify, for developing such sensing as service cloud. Okay, so next I want to give you a quick review for some existing systems, existing solutions, and also more importantly, I want to point out their shortcomings. Okay, so basically in this paper 5, you can actually find out the paper if you read our paper. Okay, this is the number 5 reference in our paper. These are researchers, a group of several researchers from Microsoft Research. They present a platform they call it Prism. Okay, in this platform they actually allow the application writer to pack their application as executable binaries and push them automatically to a set of mobile phones. Okay, and also there's some other system called another one called bubble sensing. Also nonny sensing and microblocks. Okay, they actually their functionality are pretty similar to this Prism. So next, I want to point out some of their weakness and shortcomings. Okay, so basically, this Prism system, they use executable binaries to deliver the sensing task to mobile phones. This is very platform dependent. Actually, their system only work with those Windows mobile phones. Okay, I believe the population of the Windows mobile phone user is very limited. Okay, and also may cause some security issues. Okay, it's just like you probably don't want to download any executable binary from the internet and run on your desktop, right? Because it's dangerous. It may perform some action you don't want to have. And also this nonny sense uses that system uses a customized and limitedly used Lisp dialect for implementation. So its applicability is very limited too. And also some very important issues, as I mentioned before, like energy efficiency and user incentives have not been addressed by any of those existing systems. Okay. So here is some, in this slide, actually I list some of the functionality we believe are very important for this sensing as a service cloud. Okay, we believe those functionalities should be well supported by this cloud computing system. The first one is the web interface. Okay, you always need like an interface such that the mobile, not only the mobile user, any kind of a cloud user can submit, can initiate sensing task request. Okay, and also we need some function module to actually generate, this sensing task in a standard form, such that the mobile phone can understand it. Okay, so based on the whatever information provided by the cloud user, so we also need kind of this function generating the sensing task. And as I mentioned before, this no free lunch. Okay, so this incentive mechanism is also very important. Okay, you need some functional module like a software module in your cloud computing system, which can recruit the mobile user. Okay, and I'm gonna go to some details about this a little later. Okay, another important issue is the sensing activity scheduling. Okay, because in order to achieve the power energy efficiency, you need to carefully schedule the sensing activity. Okay, let all those mobile users coordinate with each other to minimize the total power consumption while still guarantee the desired coverage. Okay, so this is also a very important function module we need in our cloud. Of course, you actually need some mobile app which actually running on your mobile phone, control the sensor to actually perform the sensing activity. So we also need this some software module to manage those sensors. And just like any other cloud, we need some storage devices, to store the data. But I believe this is nothing new here. So, but still, this is a necessary component in our cloud. All right, so next I want to introduce some design and implementation concerns. Okay, we believe the script, okay, some script written in some scripting language. Okay, in our implementation, we actually choose this scripting language called Lua. It's a fairly new one to describe the sensing task. Basically, your sensing task will be just a piece of code written in this in a certain scripting language. Okay, because we believe this is better than those executable binaries. Since scripting language, just like Java, you can consider Java as a scripting language. It can run everywhere. It can run on any kind of platform. Okay, with the help of an interpreter. Okay, so basically what you can do is to deploy an interpreter on your mobile phone, within your mobile app, which can interpret all those scripts written in a scripting language, which are actually used to describe the sensing task. We believe this better. And also you can actually use a sandbox to contain the execution of your scripts. Okay, in that way you can try to avoid some dangerous script, try to perform some danger action, to damage your phone, okay, or maybe kind of compromise your phone. Okay, so also we believe that our cloud system need to be reconfigurable. Okay, so basically, because it need to support different kind of mobile phone sensing applications, and also sometimes you may want to deploy some new scheduling policy, new incentive mechanism to the system. We need to be supported that. We need to be able to deploy those new policies very quickly. This can be achieved by those modular design and also some well-defined control messages. Also, it need to, as I mentioned before, the system need to be energy efficient. Okay, and that can be done, using those sensing scheduling algorithms. Develop some good sensing scheduling algorithm to coordinate sensing activity of the mobile users with the objective of minimize the total power consumption. Okay, so which I will introduce in greater details in the next slide. Also, we need some game theoretical incentive mechanism to actually motivate the user to engage the user in those sensing activities. Also, I will go to a little bit more details about that in the next few slides. Okay, so next I will talk about the energy efficient sensing task management. Okay, so basically our approach, we call it cloud assisted collaborative sensing for opportunistic sensing applications. Just want to point out here, for participatory sensing, basically you can do nothing about the sensing scheduling, because the whole sensing activity are fully controlled by the mobile user. Okay, they manually control when, where, and how to perform those sensings. So this problem is only for those opportunistic sensing applications. Okay, so basically we propose to use the cloud as or more specifically, using those sensing servers as a coordinator to control the sensing activity of the mobile users. So basically, the sensing server can coordinate the activity, manage them, and dispatch the task to the mobile user. But a unique challenge for the mobile phone sensing scheduling is the mobility of the mobile user are totally uncontrollable. Okay, it's different from so-called mobile sensor network. It's quite a bit of kind of research, for those so-called mobile sensor network. But most of the work on that topic assume the mobility of the mobile sensor is controllable. You can control their mobility. You can move there to wherever you want to move them. Okay. However, in this scenario, in this mobile phone sensing application scenario, the mobility is uncontrollable. Okay. So basically, in this paper, in this new Infocom 2012 paper, we did a feasibility study. We want to study if we suppose we have a cloud. It's a feasibility study. Okay. At that time, we don't even have the system yet, but we just want to study if we have a cloud to coordinate the sensing activity, to schedule the mobile user sensing activity, can it save power? If it can, how much power saving can be achieved? So we actually performed such a feasibility study in our recent Infocom 2012 paper. So here are some contributions and findings, in that paper. We basically present some polynomial time optimal algorithm, okay, to find the minimum energy sensing schedule. But based on very strong assumption, that assumption is that we have to assume that we know the moving trajectory of each every user in advance. Okay, that's obviously unrealistic. Okay, so I can admit that. However, we want to use this optimal algorithm to serve as a guideline for future design, like a practical algorithm. Okay, and also we want the corresponding optimal solution to serve as a benchmark to show how much power we can potentially save using this so-called cloud-assisted collaborative sensing. But in that paper, we actually also present some practical heuristic algorithm based on those optimal algorithm without assuming the using trajectory are known in advance. Okay, and here's some interesting findings. It has been shown by some simulation result based on the real data, the real location and the power consumption data. We actually use a Google map to provide the real location data. We actually use this so-called monsoon monitor to measure the sensing power consumption. And it shows that this cloud-assisted collaborative sensing can achieve over 80% power saving, compared with a baseline solution in which there's no such cloud and the sensing. So basically, every mobile user just periodically perform those sensing actions. Here's just one figure from our Infocom 2012 paper. Basically, this kind of a pink line show the baseline solution. The y-axis is basically total energy consumption. The x-axis is the number of the mobile users we have in the network. And the other three, actually 4 lines, actually correspond to our solution. As you can see, our cloud-assisted collaborative sensing solution actually can significantly reduce the total power consumption compared with the baseline without the collaborations among all those mobile users. And as I mentioned before, on average, we can actually achieve more than 80% power savings. All right, so next I want to talk about the incentive mechanism design. So here's some solution we had so far. Okay, so basically, in a very recent Mobicom paper, or Mobicom 2012 paper, we proposed actually two models for the incentive mechanism design. The first model we call the platform-centric model, because the second one we call the user-centric model. In this platform-centric model, basically the cloud computing platform, this sensing as a service cloud, have total control over the sensing activity. Okay, and also basically this cloud platform, it will name a price, a total payment, and all those mobile users, they compute with each other to get this some kind of contract to sense and also get their payment. Okay. In another model, this user-centric model, basically each mobile user, they name their price. It's a reserved price. Okay. So basically the platform will select a subset of a mobile user. And also we need to guarantee that every mobile user final price, the payment they got finally, will be no less than the user's reserved price. Okay. So basically for this platform-centric model, we propose a stackboard game to model this type of platform. And also we actually propose a polynomial time algorithm to compute a stackboard equilibrium. And also for this user-centric model, we design an auction-based incentive mechanism for the user-centric model, and it's computational efficient, it's profitable, and also it's truthful. So this is so far we have. So last, I want to point out some future research directions. So obviously, the most important thing is to design and implement such a system. Okay, we already did, but of course, you can maybe come up with another type of design and implement them in a more efficient way. Okay. Another important issues we actually planning to address is this, we call it GPS-less sensing task scheduling on a sensing server. Okay, so basically everybody knows that GPS is very power hungry. However, most of the sensing applications are location related. So the goal is to not to use the GPS, but still guarantee certain accuracy and coverage. Okay, for the mobile phone sensing. And also, as you may realize, so basically this system is like a multiple-to-multiple system. Okay, on one hand, every sensing task will be dispatched to a large number of mobile users which happen to be in that area of interest. On the other hand, every mobile phone may need to undertake multiple different sensing service. Okay, so we actually did some work on this sensing task scheduling on this cloud side, but we haven't done anything about this energy efficient sensing task scheduling on a mobile phone, because every mobile phone also need to undertake multiple sensing tasks. How to schedule them is also a interesting question. Also, design some incentive mechanism with a desirable economic property for some more realistic utility function will be another interesting problem worth studying. Also, the very last kind of problem we try to point out is this so-called mobile user reputation ranking and truthfulness issues. This is actually a very critical issue we haven't addressed yet. Okay, and we believe this is very important because the mobile phone users, okay, you cannot fully trust them. They may provide false data. For example, you want mobile user to sense some Wi-Fi signal strength. Okay, they may just intentionally, provide you some false data, which may mislead you. Okay, so then how can tell if those results are truthful, trustful or not? This is a very critical issue. All right, so I believe that's all. Thank you. Any question?